And we're back at it. And we are back at it looking at probability. And for us to look at probability, you're probably very familiar with the probability of one event happening and looking at counting outcomes out of the total number of possible outcomes. Those probabilities are not probably difficult for you. But what happens when two events happen possibly simultaneously? Then we get this picture. This is the very standard Venn diagram. This is the very standard Venn diagram in which the circle on the left represents some event A, and the circle on the right represents some event B. Now the space in the middle is what we refer to as A intersect B. This is sort of like A and B. So if A are all the people in the world who are women, and B is all the people in the world who are tall, then A intersect B are all of the tall women in the world. This area is referred to as a union B. A union B is like a OR B. It's read A union B, but think A or B. If A is a set of all women in the world and B is a set of all tall people in the world, obviously there are some tall women. The blue area would represent all of the people who are either women or tall or both. So it could be a tall woman, it could be a short woman, it could be a tall man, anyone who is either a woman or tall or both. One other bit of vocabulary, we could talk about a complement. That's an apostrophe up in the air. That's an A complement. When we say A complement, we mean all of the stuff that is not in A. Think not A. Everything that is not in A. So there are some things you should be able to shade on a Venn diagram. You should be able to shade A intersect B, if through no other means by rewinding this not too far. A union B complement. This would be all of the elements that are in A or not in B, or both. You should know how to shade A intersect B complement, complement. Nope, that is not what I wanted you to do. That's what I wanted you to do. A intersect B complement. So this would be all the stuff that is not in A intersect B. And then you should know how to shade in A union B complement, complement. So that's all the stuff that's not in this set. And I think you'll figure out how that goes. Okay, so what do we do with these Venn diagrams? Well, let's pretend that there are 100 students, and we ask these 100 students what language they study, and we find out that 40 of them study French, and we find out that 80 of them study Spanish, and we find out that, I don't know, 20 students study neither French nor Spanish. Now you're thinking, wait a sec. Oh, that's a terrible example. It's a terrible example. 10 study neither French nor Spanish. And you're thinking to yourself, wait a second. That's 40 and 80 and 10. That's 130 people. Yeah, well, yeah, how can we have 130 people if we have 100 people? Well, here's the thing. Some people might study French and Spanish. Some people might be in here. See, for sure 10 people are out there. And that leaves 90 people in here. So I've got 40 that study French and 80 that study Spanish. That's 120. Some of those 120 are people who got counted twice. How do I know who got counted twice? Well, I subtract out the 90 students that are left, and I get 30. And that 30 is the number of people who study both French and Spanish. And then I think to myself, if 40 people study French and 30 of them are already here, and if 80 people study Spanish and 30 of them are already here, and you can tell really quick, 10, 30, 50, 10, that's 100 people. So this is the Venn diagram that satisfies this and this and this, and we've got it. So I can ask questions like, what is the probability of studying French and Spanish? Well, the probability of studying French and Spanish appears to be 30 out of 100. And I could ask, what's the probability of studying French or Spanish? The probability of studying French or Spanish appears to be 90 out of 100. Reasonable? Reasonable? Great. So what now? Here's the thing. Sometimes two events happen. And like you're going to a carnival and you're playing a game, and in the carnival game you got to roll a die and you got to flip a coin, and if you get a tail and a 4, you're a winner. Now, we recognize that these things only happen in carnivals that are run by mathematicians, but it could happen. It's reasonable for it to happen. And the thing we recognize about flipping a coin and rolling a die is that this event doesn't have anything to do with that event. And if this event doesn't have anything to do with that event, then the events are what we call independent. Oh, whoa, that's not what we want. They are independent events. If two events are independent, then the probability of two events happening simultaneously is the same as the probability of the one times the probability of the other. That's what we mean when we say that two events are independent. If two events are independent, the probability of their intersection is the same as the probability of A times the probability of B, which means in this case, the probability of studying French is 40 out of 100. Well, we all know that that's 4 in 10. And the probability of studying Spanish is 80 out of 100, or 8 in 10. That product is 32 out of 100, which is not that. And so we can say that studying French and studying Spanish are not independent events. Because if the events were independent, then this product would equal that intersection's probability. The other thing we should talk about is the probability of two combined events happening. The probability of A union B. So I have two events. Maybe they're independent, maybe they're not. This works for all events. Maybe they're independent, maybe they're not. And it doesn't really matter. The probability of A union B is the probability of A plus the probability of B minus the probability of A intersect B. And you may ask, rightfully so, why does that work? And I say that works because here's A and here's B. If I add those two together, something has been counted twice. What has been counted twice? The intersection. And so we subtract that out. That will work all the time. So if that's the case, then I can give you this question, and you can do it with no problem. A and B are independent events. The probability of A is 1/2, and the probability of B is 2/3. You can most definitely find the probability of their intersection and the probability of their union. That is most definitely possible. In fact, you've probably just done it. In fact, that's probably it. Great! One more thing to look at, and that's the probability of A given B. There's a formula that says the probability of A given B is the probability of A intersect B over the probability of B. Now, what do we mean by A given B? This is the probability of A given B. In this scenario, we assume that B has happened, and we find the probability that A will happen given that B has happened. So let's consider the following. We'll consider the following. Bill Nye the Science Guy. Great. So sometimes the sun shines and sometimes the sun does not shine. And let's pretend that in your town of Springfield, the sun shines a lot of the time. If the sun shines, you might go to the beach. Of course, you may not go to the beach, but if the sun shines, you're definitely going to the beach much more often. Let's say you go to the beach 60% of the time when the sun shines. It's 40% of the time you don't go to the beach if the sun shines, you do something else. Similarly, if there's no sun, you might go to the beach because nobody's there, but that's kind of rare. More often than not, if the sun doesn't shine, you don't go to the beach. It's kind of the way that goes. This is the probability that you go to the beach given that it is sunny. This is the probability that you go to the beach given that it is not sunny. But my question is, what is the probability that it is sunny given that you go to the beach? That's my question. And that's an interesting question. To do that, I need the probability of being sunny and going to the beach, and I need the probability of going to the beach. And we can get all of that right off of this tree diagram. The probability of being sunny and going to the beach is the same as the probability of going to the beach and being sunny. Well, this is the branch where we go to the beach and it's sunny. And so we figure out the probability of the intersection by multiplying those together. Then our denominator is the probability of going to the beach. Well, we go to the beach on this branch. We also go to the beach on this branch. So not only is this part of the probability of going to the beach, but so is that. And whatever this fraction turns out to be is the probability we're looking for. That's 48 out of 54, and that's 8/9, about 89%. 88.9% of the time, if it was sunny, no, if you went to the beach, then it was sunny. And that seems to be borne out by the statistics that we have in the table. Well, the probabilities that we assumed in the table. Okay? It is very common on exams in probability to have to do conditional probability questions. Conditional probability questions always can be done with a tree diagram. I would strongly encourage you to use a tree diagram to your advantage. This is the kind of thing that you can work out with a teacher, and I hope that you do. Thanks for watching. See you soon.